All right, in this video, we're going to take a look at the Routing Information Protocol, or RIP. All right, one of the two basic protocols for routing, the other one being OSPF. And our goal is here when we say routing is this is not a protocol that actually routes messages from one network to another. It's a protocol that actually generates routing tables, right? It's a little confusing, but to route something versus routing, when we talk about routing protocols, we're really talking about protocols that determine these pathways, how you would route messages from one network to another. All right, so my basic drawing here, which is similar to what's in the ebook, essentially represents routers and their interconnections. The networks themselves, you can really think of as being in these lines here, these connections. So maybe more accurately, I could put like a little cloud or something in each one of these connections to represent the network. But the idea is there's a network and is connected to router A, and it's also connected to router C. Right, here's a network and it's connected to A and to B. Right. So what's really important here is for each router in its routing table to know how to get to those particular networks and what interface they're connected out of. One thing I added that wasn't in the ebook drawing is I put interface numbers, just 0, 1, or 0, 1, and 2 if it has 3 interfaces, so that we know, and this is something that's actually kept in the routing table, so that we know which interface it's connected to. What you usually see in the routing table is maybe the MAC address of the interface instead of a 0, 1, or 2. But it's the same idea, some sort of addressing or method of identifying that interface on the router. All right, so initially, what we're going to look at is machine A. And initially, A has a routing table that's going to look something like this. This is a little bit simplified, but here's the basic idea, is that A's routing table is going to keep track of the destination networks, or I'm really referring here to the routers themselves, and how A can connect to those. So it can connect to router B through its interface 1, right? So here A's interface 1 is connected to B. And the cost is 1 for each of these connections. Now, the key with routing interface protocol, one of the key aspects, is that in RIP, everything is hop based, right? In other words, the cost of transmitting any message is based on how many hops through how many routers it has to make. So the idea being that from A to C, that's 1 hop, right? From A to E, that's 2 hops, right? So A to C is going to cost less than A to E. And the cost, again, of any hop is just treated as 1. This is a little bit different with OSPF. Okay, so we start off with a routing table that looks like this for A. Realize, of course, that B also has a routing table that contains information on A and D. Router C is going to have a routing table that initially has information on A, D, and E. Router E has information on C and D. Router D has information on B, C, and E, etc., etc. Right? So every router is aware of its immediate surroundings. And we're going to kind of assume, although it's not really likely or even possible in real-world situations, that these routers are kind of all powering up at roughly the same time. So they're all starting with a basically empty routing table, or empty except for its known neighbors. Now, the way routing information protocol works is every few minutes, and usually this is configurable on most systems. 12 to 15 seems to be normal, but you can go for a shorter period of time. This is one of those network configuration issues where you kind of have to consider how often your network is going to change versus the amount of traffic you're going to generate, right? So if your network really never changes, once you reach convergence, which is where every machine has a full and correct routing table. In other words, when A knows about every other network on this entire network, and every other network knows about every other network, then the entire network has converged, right? Everything has correct information. Once that happens, if the network really never ever changes, there's not a great deal of need for transmitting a lot of traffic. So, once I've got all the information about the network all across this existing network, in other words, A through E know about everybody else. Unless one of the network connections goes down, right? If D goes down, then I need to regenerate an image of the entire network. But if that doesn't typically happen, then there's no need. All right. On the other hand, you don't want to wait a really long time because something like that could happen, right? So you want some reasonable amount of time in there. On the other hand, look at it this way. If I send information about the network across the network rather often, I'm going to be generating a lot of RIP traffic. Okay, now, modern day networks typically have bandwidth that you're going to be able to handle this. The RIP traffic isn't going to be that enormous. Once upon a time, when you were talking about very, very slow networks, there was an issue with let's not generate a lot of RIP traffic. Okay. But there is a balance you have to go with. A lot of times when you're configuring, say, Windows networks, you just kind of go with the default. But you can go in and modify that. Okay, so here's what's going to happen. I've got this initial routing table, and every couple minutes, and of course each router is doing this independently, so this isn't all going to happen at the same time. Although in my example, we're kind of assuming it happens roughly at the same time. But it really won't. Okay. Every router is going to send to its neighbors a copy of its routing table. Okay? So let's say 10 minutes have passed. A is going to send B and C a copy of its routing table. Okay? Now, most importantly for A, though, C and B are going to send to A copies of their routing tables. And so what's going to happen, we can maybe type this up. Let me bring it over here. We can type this up. So C's routing table is going to look something like this. So C knows about A, D, and E. Okay. And C knows that, this is not terribly important for us here, but C knows that A is off of its interface 0, and C knows that D is off of its interface 1. Okay, oops. And C knows that network E, or router E, is off of its interface 2. And of course, from C to each of these, the cost is 1. All right, so what we're looking at now is that moment when C sends its routing table to A. All right, so what happens then is A receives all this information from C and is going to analyze it. Not necessarily mean to do that. Going to analyze it and look at the destination networks. And what it's looking at is there information in this routing table that it doesn't know about, in which case it's going to add it to its routing table, or if it finds information that shows a shorter path to something, it's going to add that to its own table. Okay, so first of all, there's information about A. Now A realizes, oh, this is myself, so it doesn't do anything with that information. Okay, but then it sees this information for D. Now it currently doesn't have any information stored about D, so it's going to go in and actually add this. Okay, so it adds network D. Now the interface to get to D depends on where A got this information. And of course, A got this information from C. A knows that C is off of its own interface 0. So this information coming in from C is also going to be available off of interface 0. All right? Now, the cost, A knows that to get to C, it costs 1. C is telling it that to get on to D, it's going to cost 1. So 1 plus 1 is 2. All right, the next piece of information C delivers to A is about network E. All right, A doesn't know anything about network E, so it adds E to its routing table. All right, again, to get to E, I have to go through C, and to get to C, that's interface 0. Right, and again, the cost to get to C is 1. To get from C to E, that's another 1, so it's a total of 2. All right, so after I transfer information from C, I now have a picture of the network that looks like this. I know about B, C, D, and E. Actually, I know the entire network now. And I know that I can get to D and E through C at a cost of 2. Okay, now, there's also going to be information coming from B. Let me put B's in here. I don't know that I'm going to get any new information, but B knows about A, and let's see, A is off of B's interface 0, and that's going to be a cost of 1. And B also knows about D. D is located off of B's interface 1, and that's also going to cost 1. Okay, so now when this information comes from B, I find out about A. Well, again, I am A, right? So I'm not going to do anything with that information. But now I find out about D. Now notice, notice that D is going to cost 1 to get from B to get from B to D is going to cost 1. To get to B is going to cost 1. So I know this path tells me that D is available in 2, right? But that's no better than what I already know, right? D here, I can go through interface 0 to get to D at a cost of 2. This is telling me I can go through B, which is interface 1, to get to D for a cost of 2. That's no better. So unless there's some other reason as far as cost is concerned with RIP, there's no reason to actually change anything or add anything onto our routing table. Okay, so to make this slightly more interesting, I've gone in and I've added router F, right? And router F is connected to E. Okay, so after this first transfer of data, C, which knew about, I realized I just made a mistake. C, which knew about A, D, and E, transferred that information to A. So A has added information on D and E into its routing table. Here, I'm looking at something that's off the screen. There you go. So A, this is A's routing table. A has added D and E. All right. B also told A about D. A already knew about D, right? Knew that there was a path of 2. So it didn't actually make any changes. Now, in the meantime, though, E, way out on the end, knows about C, D, and F, right? When E transfers its information, it transfers its information to C and D. That's when C and D know about F, okay? So let's say we kind of have to keep track of all these routing tables. All right, but here's D's routing table. D's initial routing table had, I'll type it up over here while I'm looking at the screen. B, which was off of D's interface 0, and that was a hop of 1. D knows about C, which is off interface 1, and that's a hop of 1. And it knows about E, which is off of D's interface 2, and that's also a hop of 1. Okay, so there's D's initial routing table. Now, after E passes its information to C and D, okay, D is going to find out about F. So D is going to add F. F is available off the same interface as E, right? Because E is the device that's actually sending the information to D. So it's off of 2, and it has a cost of 2. Because to get from D to F, you got to go through E. Meanwhile, E is also sending this information to C. So C is discovering F, right, through E, which is off of its interface 1 at a cost of 2. Okay. So now C and D know about F. All right. The next time data is transferred, all right, let's start with C. C is going to transfer its data to E, D, and A, right? So C, now this is really the second transfer, right? Because C has already transferred some data over there, so A found out about E. Now C knows about F, so the second time it transfers data, which could be, you know, if you set the data transfers to happen every 5 minutes, this means 10 minutes later, right? C is transferring information about F. Okay, so C basically sends its entire routing table now to A. Okay, what does A find out? Well, A finds out about itself, right? A finds out about this path through C to get to D. All right. A already has a path. It was a path to D. A already knows about a path to D that costs 2. Okay. This path that C is advertising is also going to cost 2, so that's no better. Now you realize from earlier that that path to D it may have come from B, it may have come from C, I don't remember. But you notice up here in A's table, we don't really keep track of how you get to that final destination, right? The only thing we know about D, the only thing A knows about D, is that D is available off of A's interface 0. From there on, we got no idea, right? And in fact, I guess A does know how to get to D through C, right? So this is C re-advertising a path to D, but A doesn't know that its current path to D goes through C. It just knows it goes out interface 0. All right? Does that make sense? In other words, we're not keeping track of like step by step how to get to the end. All A needs to know is if I have something bound for D, I just send it out interface 0. And it's up to whoever is on the other end of interface 0 to keep track of it. Now, probably in your routing table, you actually have a destination IP address, which is going to be the IP address of C's interface 0. Right? So in other words, if A is going to be sending out its interface 0, it needs to know the address of something on the other side. So to some extent, we are keeping track of that. But we're not keeping track of the full path to D. We just know to get it there, we send it this way, and then it's up to that router to forward it on to the next correct location. Okay, so the next thing we get from C is information about E. This information about E is going to take 2 hops. We already know information about E that takes 2 hops, so we don't make a change, right? But what we do find out is that there's a router F out there, okay? Now again, router F, we found out about F through network C, so we know that's off interface 0. And of course, C knows to get to F costs 2 hops, so A is going to record that it's going to take 3 hops to get to F. All right. Meanwhile, C is no, wait a minute. D. What happened? D transferred its information to B. All right. Okay. I was just making sure this was going to work. All right, so D has transferred its information to B. Now B has already knows about A, already knows about D. B is also going to learn about E, which is off of its interface for D, and is going to take 2 hops, right? And B also learns about F, which is also off of its interface for D, but is going to take 3 hops. Okay, so now when B transfers its information to A, right, again, A looks at this as, well, I'm A, so I don't care about that. D, I know how to get to D already, and it takes 2 hops, so this path is no better, right? E, it finds out, it already knows about, but it also finds another path here with B. But again, this is going through B, which already takes 1 hop. So what this is saying is to get to E is going to take 3 hops. Now it already knows a path that's only going to take 2 hops, right? So it's not going to add that information to its routing table. Then it also finds out about F. But to get to F through B is going to take 4 hops. It already has a path to F with 3 hops, so it's not going to make any change there, right? The only way it would make a change is, let's say, how can we short circuit this? If we knew that there was actually a path from B to F, right? And so B already had a path maybe out its interface 2, let's say, and it's 1, right? So in that point, if B advertised that it had a path to F, then that path to F cost 1 from B. To get to B cost 1, so that's a path of 2, which is better than the thing I already know about. Okay, so if B advertised a shorter path, then I'd go in and change the interface, because now I know that to get to F, I need to go through B, and I change the hop count now to 2. Okay, that is if it turns out there was a shorter way to get to F through B than going through C or going from B to D. Okay, all right, so to summarize, the basis of RIP is essentially these periodic transfers of the entire routing table. Every device sends its entire routing table to every one of its neighbors. All right. So you realize it is very, very simple and easy to put together routing tables. The big issue with RIP is that it can be, possibly some period of time before messages get transferred, information gets transferred from one end of a very large network to another. Right? It took, E knew about F, forgetting this shortcut for a second. E knew about F, E told C and D about F, and then C and D told A and B about F. So it took 2 transfers of data for the entire network to converge, knowing that F is there. And of course, we didn't follow it the other way, but A and B were known to, A was known to C, B was known to D, right? Then on the next data transfer, C learns about B, D learns about A, and E should learn about A and B. And then on the next data transfer, F will learn about A and B. Right? So of course it goes both ways. Right? So you have that convergence period. You can have this short amount of time, hopefully short, where not every network knows about every other network that's available. One more pro, I guess, though, is that the amount of traffic generated by RIP is usually not all that bad, and it's localized, right? Because A is only going to send stuff to B and C, right? So no matter how big its routing table gets, it's only going to be clogging up this connection and that connection, right? All the others are going to do the same, but we're not sending like the entire routing table to every other machine on the network, right? It's not a broadcast. It's a unicast from A to C and A to B. Okay, so that's RIP.